Hello guys, welcome to Calc 2. This is 10.7 power series. This is a new type of series that we're going to look at. So a power series has the general form, infinite sum of some constant Cn times x to the power of n, and then n increase from 0 to infinity. All right, so like a really simple example would be like a polynomial. Let's say um, 3x squared minus 2x plus 1, right? Then we can write that as a power series that looks like this, and going from 0 to 2 of Cn and xn, right? And then in this case, C0 would be 1, C1 would be -2, and C2 would be 3, right? So all the c's are the coefficients of the polynomial, right? We can see that this is actually of a form of a polynomial, right? So all the cn's are your coefficients of the series, right? Which is what it's called. Okay. Now, for each x value, for each fixed x value, the series above is a series of constant that we can test for convergence or divergence, right? For example, maybe when x is equal to 1, it will converge, right? But if we change x to 2, maybe it will diverge, right? So depending on the value of x, the series can both diverge or converge. Power series may converge for some value of x and diverge for other values of x, right? So it's not always converging as well as not always diverging. It actually depends on the value of x um, to determine whether it converges or diverges. Now, if we look at the sum of the function, the sum of the series is actually a function, right, whose domain is a set of all x which the series will converge. Okay, so this is how we define our domain, is a set of the x value that we will get our series to converge. Now notice that this function that we are looking at looks like a polynomial, right? But it has infinitely many terms, like a polynomial with infinitely many terms. Okay, so let's look at some scenario, right? If all the cn's are equal to 1, then we have a really nice infinite sum, and we get this, right? If all the coefficients of the series are equal to 1, then we get this infinite sum, right? Notice that this is actually a geometric series with r equal to x, right? So this is actually a power series that we're looking at, power series that looks like geometric series. Therefore, we can say that this power series will converge for any absolute value of x less than 1, and diverge for all other x, right? Because we know geometric series converge when the rate or the r is the absolute value of r is less than or less than 1, and it's going to diverge for everything else. All right, so a is 1 and r is x. Therefore, the infinite sum, we can find that as a over 1 minus r, which is 1 over 1 minus x. So what we can do here, what we can say here is that this actually represents the infinite sum for this power series when the coefficients are equal to 1, right? So we will get this result, right? 1 over 1 minus x is equal to this infinite sum. this infinite polynomial, right? Where all the coefficients are 1, or the infinite sum of x to the n. So notice that what we have done is that we started with some infinite series, and then we can represent it with some function. Okay, and that is something very interesting. Okay, we can represent an infinite series using a function, or vice versa, we can represent a function using an infinite series. Now, in a more general sense, if we have a series of this form, which is pretty similar to what we had earlier, except with this x minus a, right? Then we say that this is a power series centered at a, or a power series about the value of a, right? Where a is some constant. Okay? And we can use a ratio or root test to find out what value of x the series will converge. All right, let's say if I take the limit as n approaches infinity of the absolute value of an plus 1 over an is equal to L. Now, if we can show that this is less than 1, then we can show that it's convergent. Right. So what we're going to do is basically we'll put them in a ratio test or a root test, and we're going to solve for absolute value of x minus a to get absolute value of x minus a is less than some constant r, right? And this r is actually based on what type of series you have. And this r has a specific name. It's called the radius of convergence, or ROC for short. Okay, so basically, as long as your x value will make absolute value of x minus a within this radius of convergence, then the whole series will converge, right? And furthermore, to solve this inequality, all we need to do is it's like solving an absolute value inequality, right? So negative r is less than x minus a is less than r, and then we get negative r, a minus r, capital lowercase a minus r is less than x, is less than a plus r, right? So within this interval, if x value is within this interval, then we are going to get convergence. And this interval has also a specific name. It's called the interval of convergence, or IOC for short, right? So IOC, interval of convergence, actually comes from ROC, the radius of convergence. After you have identified the interval of convergence, we know that x value is for the x value within the interval of convergence, we are going to get a converging power series. Now, another thing that you want to do is you want to check the endpoints, right? At a minus r and a plus r, and see if they converge at the endpoint as well, right? So if it's convergent, then we use brackets to include the endpoint to show that it's also converging at the endpoint. Now, if it's divergent at the endpoint, then we use parentheses to exclude those endpoints that are diverging. Now, notice, remember that they won't both behave the same way. Sometimes one endpoint will converge and the other endpoint will diverge. So we want to be very careful on when to use brackets and when to use parentheses. All right, so our first example, find the radius of convergence and the interval of convergence. Okay, so think about a ratio or root test. Which one are we going to use? So for this one, I think a ratio test would probably work well. So let's try that. So ratio test, limit as n approaches infinity of an plus 1 over an, right? That will look like. So since we have the absolute value, we don't have to worry about -1, but let's write it down. Okay, -1 to the n plus 1, n plus 1 square, x to the power of n plus 1, all over 2 to the n plus 1, multiplied by the reciprocal of an, which is 2n, -1 to the n square, and x to the nth power. All right, so let's reorder them a little bit so we can clear things up a little easier. So -1 to the n plus 1 over -1 to the n, multiplied by 2 to the n over 2 to the n plus 1, multiplied by n plus 1 square over n square, and then last but not least, x to the n plus 1 over x to the n. All right, so we have a lot of things that we can simplify out. All right, so the first factor, right, we have one extra -1 in the numerator, right? So we can do that, one extra -1. For twos, we have one extra 2 in the denominator, right? So let's do that. Nothing we can do with the third factor. And the fourth factor, we have one extra x in the numerator, right? So let's cross out stuff like that. All right, and let's see what we have left, right? So we have limit of -1 times n plus 1 square x all over 2, right? And when you take the limit to n square, right? When you take the limit as n approaches infinity, right, the only term that's going to give us trouble is the n plus 1 square, n over n square. Now, since they have the same degree, right? So the limit as n approaches infinity will just be the ratio of the leading coefficient. That is the absolute value of -x over 2. Okay. All right. So this is the result from our ratio test. Now, in order to figure out the radius of convergence, or before that, in order for the ratio test to be converging, this has to be less than equal to 1. Right? Let's put down a note here. Ratio and root test converge for limit to be less than 1. Okay. All right, so let's do this. Now, in order to find radius of convergence, it has to be in the form of x minus a, less than some value, right? The coefficient of x has to be 1. All right, so let's see what we can do here with absolute value of -x over 2 is less than 1. Now, notice that this is still not in the form of radius of convergence, so there's some work to be done. First, let me bring out the -1 over 2 outside of the absolute value. So I have 1/2 times the absolute value of x less than 1. Now, this is still not in the form of radius of convergence, right? Specifically, we want this to be absolute value of x minus a by itself and everything else on the other side. All right, so let's multiply the 2 to the right-hand side. I get absolute value of x less than 2. Okay. And now this is in the form of radius of convergence with the value of a equal to 0, right? So this is your radius of convergence. Absolute value of x is less than 2. All right, and then to do that, to find out the interval of convergence, all we need to do is, solve the absolute value inequality, right? So we get -2 is less than x is less than 2. Okay. So this is our proposed interval of convergence, right? Now remember that after we found the interval of convergence, let's go back a little bit, we also want to check the endpoints, right? Check the endpoints for convergence or divergence so that we know whether to include them or not. All right, so next, check endpoint. X equal to -2 and x equal to 2. All right, so let's do x equal to 2 first. All right, now if x equal to 2, we have to plug that into our original power series. Let me copy that down here. All right, so when x is equal to 2 into the original series, we have something like this. And is equal to 1, infinity, -1 to the n squared, 2 to the n, over 2 to the n, right? And then we can simplify the 2 to the n. That will give us n is equal to 1, and then -1 to the n and n squared, right? And this just looks so diverging, right, in so many sense, right? First, n squared, that's just gonna go up to infinity and infinity, right? So to make sure that we show this rigorously, let's just use test for divergence. Right, so take limit as n approaches infinity, and we want to show that either does not exist or is not equal to 0. Right, so -1 to the n square. Okay, so that's going to give you a lot of trouble, right? The n squared is going to go off to infinity, and then we have the alternating factor of -1 to the n, right? Alternating. Right, so we can say that this limit does not exist. So what does that mean? That means power series, the original power series that we have, will diverge at x equal to 2. Okay, so we took care of one endpoint. X equal to 2 will diverge. Right, and let's check x equal to -2. X equal to -2. So do the same thing. Replace the x with -2 in here. Right, equal to 1. -1 to the n squared, -2 to the n, and then 2 to the n. All right, so let's do a little bit of clearing up. I'm going to rewrite -2 to the n as -1 to the n times 2 to the n over n, 2 to the n. All right, so you can see that we also have some things we can clear up. All right, first 2n. Right. And then I'm going to multiply the -1 to the n and -1 to the n together to get -1 to the 2n times n squared. Now, -1 to the 2n is actually always 1, right? Because we're always taking -1 to some even power. So we just have n is equal to 1 and then n squared. Now, n squared, that's going to diverge, right? Because again, by test for divergence, we can just take the limit as n approaches infinity, and this is going to go to infinity, right? So diverge for x equal to -2. All right, so for both the endpoints x equal to 2 and x equal to -2, they both diverge. Therefore, we can summarize our final answer. First, starting with the radius of convergence. Let's go up. We saw that earlier, right here. Radius of convergence is 2, right here. Capital R is equal to 2. And we also have the interval of convergence, which was from -2 to +2. And we also check the endpoints that they are both diverging at 2 and -2, right? So our interval of convergence would just be parentheses -2 to 2. Okay. So let me draw this on a real line, and hopefully I can give you a better idea. All right, so that's 0, that's a -2, that's 2. The power series is converging between -2 and 2, but not including -2 and 2, right here. So by looking at this interval, if you look at the middle point, right, exactly right in the middle, we get 0, right? And from 0 to each of the endpoints, it's a distance of 2. And that's where the radius of convergence comes into play, right? Radius of convergence is how far you are away from the center to get converging x values, right? And then, of course, the interval is based on what we solved from the ratio or root test. Now, let's say in this case, the center is not equal to 0, right? Remember that earlier we say that, go up a little bit more, right? This little a, x minus a in here, it's called the center of the power series, center about at a, or power series about a. Now in our example here, our center is actually a 0 because we don't have an a here. A is equal to 0, right? So that's why it's center at 0 with radius of 2. So we see to the left of 2 is, to the left of 0 by 2 units, it's -2. And to the right of 0 by 2 units, it's +2. And that's how we get the radius of convergence and the interval of convergence. All right, let's do this next one together. Again, we're going to use the ratio test. All right, so 3 to the m plus 1, x plus 4 to the m plus 1 all over square root of m plus 1. All right, that's a n plus 1, and then we need a n reciprocal. So square root of n, 3 to the n, x plus 4 to the n. All right, so before we move on, actually, there's something that I want to point out. I noticed that we have an x plus 4, right? That means our center is going to be a little different, right? And we'll see that in a second. Okay, next, again, let's clean something up. Three to the n plus 1, and then x plus 4 over x plus 4 to the n, and then the square root of n. All right, and let's cross out some stuff. We have an extra 3 in the numerator, an extra n plus 4 in the numerator, and nothing else we can do here. Okay, all right, let's see what we have. So 3 x plus 4 times radical n over radical n plus 1. All right, so the only part that's going to be affected by the limit as n approaching infinity is this part right here. Right? And since they have the same degree, that actually will go to 1, right? This whole thing will go to 1. Right? So our limit becomes absolute value of 3 times x plus 4. And again, when is the ratio test converging? When the limit is less than 1. All right. So next, we are going to use this inequality that we have here to figure out the radius of convergence and the interval of convergence. And let's do a quick, again, I want to mention this again because it's very important. Radius of convergence has to be in the form of absolute value of x minus a less than some capital R, right? And this capital R is going to be your radius of convergence. Okay, so let's see. 3 absolute value of 3, x plus 4 less than 1. So this is not in the form of a radius of convergence yet, right? We have this extra 3 in front of here, else we would have the form x minus a. All right, so let's bring out the 3 outside of the absolute value. Divide by 3. There you go. And this is in the form of radius of convergence, right? ROC is equal to 1/3, right? Centered where? Centered at -4, right? Because it's in the form of x minus a, and we have x plus 4 here, right? So the center is at -4. All right, good. That's one down. And then from this point on out, it's pretty straightforward, right? To find interval of convergence, all we need to do is solve this absolute value inequality, right? So we have -1/3 less than x plus 4 less than 1/3, and then you subtract 4, so you get x in the middle, and that's -12, right? So -13/3, and then on the right hand side we have -11/3. Okay, so that's our proposed interval of convergence, right? Proposed. Right. Now, the reason why I say proposed is because we still have to check the endpoint, right? Still have to check endpoint. All right. So here our endpoints are -13/3 and -11/3. Right. So let's copy down the power series down here again. All right. So let's check our endpoint, starting with -13/3. So do the same thing, plug it in to the power series, and is equal to 1, 3 to the n, -13/3 plus 4 to the power of n over radical n. All right, so let's see what we have. That's equal to 3 to the n, and then that's 12. So -1/3 to the n over radical n. Now this is we can actually combine the numerator together to get n is equal to 1, and then that will be -1 to the n power over radical n. Okay, so this is actually an alternating series, right? And if without the alternating part, 1 over square root of n, that is actually a p series, right? But we cannot say that it diverge because it's a p series with a p equal to 1/2, right? So since it's an alternating series, we have to do AST with bn equal to 1 over square root of n. So to check by alternating series test, we need to show that first bn is decreasing, right? Need to show bn decreasing and limit of bn is equal to 0, right? Which is pretty easy to show, right? So let's check the limit part first. So limit of 1 over radical n as n goes to infinity, right? That goes to 0, no problem. Let's check if it's decreasing by taking the derivative of a function that's in the form of 1 over radical x. So let f of x be equal to 1 over square root of x. Then f prime of x is going to be -1 over 2 times the square root of x cubed, right? Since it's square root, that's always negative, right? And we know that x value, the square root here is always going to be negative. All right, so there you go. And inside the square root, it's always going to be a positive number because we're looking at n in this case. So we have shown that the limit is equal to 0 and it's always decreasing. Then it will converges by the alternating series test. So what does that mean? That means when x is equal to -13/3, the power series will converge. All right. So yes. Good. All right. Now let's check the other endpoint, x equal to negative 11 over 3. All right, and a lot of writing here. You just take some time and write it down. So I'm just gonna skip it. It's by adding it. So that's 1/3 to the n power over square root of n, which is n equal to 1, and that's just 1 over radical n. Right? Now, this is not an alternating series anymore, right? This is actually a p series, right? It's a p series with p equal to 1/2, which is less than 1, therefore diverges. Okay, so one endpoint converge, right? Negative 13 over 3, it converges by the alternating series test. And the other endpoint, negative 11 over 3, is divergent because it's a p series with p equal to 1/2. Therefore, we can state our final answer, right? ROC, radius of convergence, is right here, right? R is equal to negative 1/3. Oh, 1/3, not negative 1/3. Right, an interval of convergence, it's going to be from negative 13 over 3 to negative 11 over 3, including negative 13 over 3, but not including negative 11 over 3. Okay, and I want to show you again what this looks like on the real line, right? So the center is going to be -4, right? As we saw earlier, right here, right? It's centered at -4 with radius of convergence of 1/3, right? So it's going to be converging 1/3 unit to the left of -4 and to the right of -4, right? So 1/3 to the left of -4, we get negative 13 over 3. And 1/3 to the right of -4, we get negative 11 over 3, right? But unfortunately, it only converges at one endpoint, right? One endpoint at negative 13 over 3, but not at negative 11 over 3, right? And this green interval will be our interval of convergence. Sometimes the root test can also work, right? So in cases where you can rewrite an as some bn all raised to the power of n, then the root test should be used because it makes things much easier, right? Let's see what we have here. And so the infinite series that we have, we can actually put everything together without the exponent, right? 3x minus 5 over n, and raise everything to the power of n, right? In this case, in cases like this, it's very nice to take the root test because it just takes care of the exponent out here altogether, right? So let's do the root test. Right, the nth root of the absolute value, 3 times x minus 5 over n all raised to the nth power, right? All right, and then we can just ignore the nth root and the nth power. We just have the limit of absolute value 3 times x minus 5 over n as n approaches infinity. So notice that we only have one n in the denominator, right? So when we take the limit as n approaches infinity, this whole thing goes to 0, which is less than 1. What does that mean? So think about this for a second. We haven't picked any x value. We haven't considered any x value, right? And we just take the limit from the root test and it's equal to 0, which is less than 1. Then just from here, we can say that it's converging. Always, right? Always convergent. So what does that say about the radius of convergence? It's actually infinity, right? It doesn't matter what x value we pick. There is no center. There's no center of convergence. And in this case, the interval of convergence would just be from negative infinity to positive infinity, right? Because you can pick any x value you want, and that series is always going to converge. right? Because from the root test, the limit is always equal to 0 when we perform the root test, right? That means the x value does not play any role to determine whether the power series converge or diverge. Right? So cases like this, it's very nice, right? Not a lot of work to do. Right? But this example, I just want to point out that in different cases, you can use different tests, root test or ratio test, right? For example, earlier we have, like in this case, even though the numerator we have to the power of n, denominator we have square root of n, then in that case, root test might not be a good way to go. So most of the time we will go into ratio test. Rarely when you see this where everything has something as an exponent of n or some multiple of n in the exponent, then we can use the root test, and that will make things much easier. All right, next let's look at some functions as power series. We have seen our first one from earlier, right? We were just adding up different powers of x, and then we show that the sum from it's actually a geometric series with rate r equal to x, and then the infinite sum is 1 minus x. And what we're going to do now is we're just going to play around with this, right? We can play around with what we have here, this equation, and we'll probably get something out of it. All right, so first what I'm going to do is I'm going to attempt to look at 1 plus x, right? And 1 plus x, I'm actually going to write it in a different way. I'm going to write it as 1 over 1 minus negative x, right? Now I know 1 minus x looks like this, right? Looks like the power series I have here. Now if I replace x with negative x, right? Notice that's what I did here. I replace x with negative x. Then I can rewrite the power series as the infinite sum of negative x to the nth power, right? Of course, in this case, for absolute value of x less than 1, in order for us to get a converging series. Then I can rewrite this as n equal to 0, and then negative 1 to the n times x to the n, right? And again, absolute value of x less than 1. Okay, so let's write out the first few terms and see what we have, right? So starting with 0, we have 1 minus x plus x squared minus x cubed minus x plus x to the fourth, and dot, 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 right? So it becomes an alternating power series, right? Which is kind of neat, right? All we did was replace x with negative x, and then we get this other infinite power series, right? Alternating power series, which is kind of cool, right? And there are so much more things we can do with this. Let's look at a few more. All right, so let's say we have a function f of x is equal to 1 over 1 minus x, right? Let's find f prime first, f prime of x. So when you find f prime of x, you bring down the power -1, and then the chain rule will give you another negative, so you actually get positive. That will give you, actually, I'm not gonna go that fast, right? So that's 1 minus x to the power of -1. F prime will be bring down the power, -1 times 1 minus x to the power of -2, multiplied by the chain rule, which is another -1, right? This is the chain rule. Chain rule. All right, so what we have for f prime is 1 over 1 minus x squared. Okay, now we know from earlier that 1 over 1 minus x is the infinite sum of x to the n. Now if we take derivative on the left hand side, right, we get 1 over 1 minus x quantity squared. What about the right hand side, right? Because if they are equal, then if I take derivative on one side, I should be able to take the derivative on the other side, right? So on the other side, that's just a power series, right? You bring down the n, and then you subtract the power by 1, right? Now in this case, n, instead of going from 0, it has to be from 1, right? Because it's 0, then the first term is just going to be 0, so it doesn't make sense, right? So we are going to change that to from 1 to infinity, right? And there you go. We have another set of function that can represent power series, right? And also, this is converging for absolute value of x less than 1. Okay? Because it actually came from the power series, x to the n. All right. So taking derivative, and maybe you could take integral instead of derivative. Yeah, let's try that. Right. So f of x is equal to 1 over 1 minus x. Right. Then the integral of f of x will be negative ln of 1 minus x, right, plus c. All right. So let's see. 1 over 1 minus x is the infinite sum of xn. And then we took the integral, right, integrate, to get ln, negative ln of 1 minus x. What is that equal to? Right? If you integrate that, you add the power by 1 and divide by the new power, right? And now our n is still going to be from 0 to infinity, right? Because if it's negative 1, then the denominator would just be 0, which is not going to make sense. All right, and here we have another power series representing a function, right? Negative ln of 1 minus x is equal to that. Now you can put the negative sign on the other side, right? It doesn't matter. And it's also converging for absolute value of x less than 1. Okay. Well, I forgot to cover one thing. So this c here, you can just plug in x equal to 1, right? And then to solve for c, and c is actually going to be 0. Plug in x equal to 1. And you get c is equal to 0. Oh, sorry, not equal to 1. Plug in x equal to 0 to get c equal to 0. All right. So I want to go back to these last two examples. Notice that when I took derivative and I took integration, I just look at the sum instead of term by term, right? Because they are just infinitely many terms together, right? 1 plus x squared plus x cubed, and so on, right? So if I take the derivative on the left-hand side, then I take the derivative on the right-hand side by taking them term by term, right? But since we actually have a form for the series, which is infinite sum of x to the nth power, then I can just take the derivative of x to the n, right? Treating n as a constant, bring it down, subtract the power by 1. So we can do that actually without having to go through every term, because there are infinitely many terms and who knows how long that's going to take us, right? As well as the integration, right? Instead of taking it term by term, I just look at the general form and integrate the general form, slap the sum in front of it. Okay. All right, next let's try to get let's look at one more functions to get from 1 over 1 minus x. Right? So 1 over 1 minus x is equal to the infinite sum x to the n. Right? Now I'm going to replace. Our goal is actually to look for 1 over 1 plus x squared, which I can rewrite now as 1 over 1 minus negative x squared. Right? And by doing that, I can use the same series that we had earlier and replace x with negative x squared. Okay, so let's see what we have. Like that. Negative x squared, and then to the nth power, right? And let's clean this up a little bit. We will get negative 1 to the n power, and then x to the power of 2n. And keep in mind that this is still convergent for absolute value of x less than 1. All right, so now we're getting somewhere, right? This is going to be fun. If we integrate the left-hand side, right? If we integrate this, we get arctangent x plus c, right? Next, what about the right-hand side? What do we do, right? Well, that's just a polynomial, right? The negative one just determines the sign, right? So actually, it's not going to matter. When we integrate it, we get negative 1 to the n, right? X to the power of 2n plus 1 over the new power 2n plus 1. And there we have it. We have a new expression for arctangent. Now, in order to solve for C, we can just pick solve for C, pick x equal to 0, right? When x is equal to 0, on the right-hand side, everything is going to be 0, right? Yeah, everything's going to be 0, and then arctangent of 0 is 0, so that leaves us, so 0 plus c is equal to 0 plus 0 plus 0, right? So c is equal to 0. All right. Actually, let me summarize it here. So arctangent of x is now the infinite sum of negative 1 to the nth power, x to the power of 2n plus 1, all over 2n plus 1 for absolute value of x less than 1. Okay. And actually, I'm going to write out the first few terms to just give you a feel of what we have, right? That looks like x minus x cubed over 3 plus x to the 5th over 5 minus x to 7 over 7 plus dot, 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 right? It's an alternating odd power, right? Pretty cool. All right, so let's look at a quick summary of what we have. The 4 functions that we have from today. All right. Yeah. Okay. So first we started with 1 over 1 minus x, right? Because we used the geometric sum to find out that the sum for infinite sum of x to the nth power is 1 over 1 minus x. And then to get the next one, right, we took derivative, right? And to get the third one, we integrated it, right? And to get the arctangent, we replace x with negative x squared. Right? Now, these are pretty useful, right? Once you understand it, right? It's going to give us a lot of different ways to work with functions now, because we can now represent function as infinite series, right? So I'm not going to force you guys to memorize this, but you know, you can have this as like a note somewhere, and then use it as a reference. All right, next let's look at some examples. All right, let's look at our first example. We want to represent this function as a power series. So first, we want to identify on the things that we know that we can represent as a power series. For example, this 1 minus x squared in the denominator, if we can, you know, break out the x cube and then rewrite like this, then we know that this part is actually can be represented as a power series, right? From earlier, we know that 1 over 1 minus x squared can be written as n times x to the power of n minus 1, right? We got that by taking the derivative of the first one, right, of x to the n. That means I can actually rewrite this whole thing like this, right? So f of x, I'm going to use a different color, right? So f of x is x cubed times 1 over 1 minus x squared. I can now rewrite this as x cubed times the infinite sum, n equal to 1, infinity, and x to the n minus 1. Okay. Now notice that I have an x cubed here, which is fixed, right? It's just x to the third power. The power does not change. So what I'm going to do is keep in mind that this is a series of terms, right? We have a lot of terms in here. 1 plus 2x plus 3x squared plus 4x cubed, and so on. All right, so what I'm going to do is I'm going to distribute this x cubed into here, every term, right? So every term will get an increase of x power of x by 3. That can be done by doing this, by taking this x cubed and multiply it to this term right here, right? So what we will have will look like this. Infinite sum of n times x to the cube times x to the n minus 1. And to combine these together, all we need to do is add their exponent together because they have the same base, right? So I have n equal to 1, n times x to the power of n plus 2. Okay, and that's it, right? And we're done. And since it comes from this series right here, we know that the radius of convergence will be the same, right? So the radius of convergence is equal to 1. Same as the original one, same as the one that we got. Okay. All right, let's look at a few more. All right, so here is another example. We want to find the coefficient of x to the power of 6 in the power series representation of this expression, right? 3 over 4 plus x squared. Now, this is not as nice as the previous one, right? So our goal, since we only have few to work with, we're going to try to go back to the beginning and try to get it in the form of 1 over 1 minus x, right? 1 over 1 minus x. Let's do that. Okay, so first, I'm going to factor out a 3, right? So 1 over 4 plus x squared. Right? And I want the 4 to be a 1, so I'm going to factor out a 4 from the denominator. And then I'll get 1 plus x squared over 4, like that, right? Okay, and now let me bring the 4 out. So I have 3/4 on the outside. 1 over 1 plus x squared over 4. And then I'm going to do the same technique that we did before, is I'm going to rewrite the denominator as 1 minus negative x squared over 4. Right, so now that is in the form of 1 over 1 minus x. And then what we can do is we can use the power series that we know for this one by replacing x with negative x squared over 4. All right, so let's try that. So 3 over 4, just copying this down. Here 4, 1 over 1 minus x squared, negative x squared over 4 is equal to 3 over 4. And then I'm going to replace all the terms in here with negative x squared over 4, right? So it will be 3 4 times 1 plus negative x squared over 4 plus negative x squared over 4 squared plus negative x squared over 4 cubed plus dot 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 dot. Right. So what I'm doing here is that each of these terms, right, the 1 corresponds to this one right here. The x corresponds to this one right here. The x squared is this one, and x cubed is this one. Now our goal is to find the coefficient of x to the power of 6. So I know that this is going to be the x to the power of 6, right? So I'm going to stop here, and then all I need to do is figure out the coefficient, right? So let's see. Actually, I'm going to do one more step before I pick out the coefficient. Right? So it's equal to 3 over 4, 1 minus x squared over 4 plus x squared over 16 minus x to the 4th over 16 minus x to the 6th over 64, right? And plus dot dot dot. Right, and then after you distribute the 3/4, you get 3/4 minus 3x squared over 16 plus 3x to the 4th over 64 minus 3x to the 6th over 256 plus dot 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 dot. Okay. All right. So the coefficient can be found right here. Right? Coefficient of x to the 6th power is negative 3 over 256. Okay. And we're done. Right. So this is another type of problems that you will see on the homework is it's asking you for specific coefficient on some specific terms. Right? And then this is when you need to pick some of the power series so that you can expand that function into some sort of power series, and then you can find the coefficient. Right, so in the last part of the note, I included some work that help us to approximate pi and ln of 2 using an infinite series, right? So we can just look at this pretty fast. So arctangent, we can rewrite that as an infinite series, right, as we saw earlier. And then we plug in x equal to radical 3 over 3, which is less than 1, means it's converging. So on the right-hand side, we have this infinite sum, right, adding alternating numbers. On the left-hand side, arctangent of rad 3 over 3 is pi over 6. And then you multiply the 6 to the right-hand side, you get pi, right? So pi can be represented by this infinite sum, right? And I think that's pretty cool, right? One real application for us to see that we can actually estimate pi. And you can actually use this technique to approximate a bunch of different values, right? For example, E can be done this way, right? And then on the right-hand side here, we have ln of 2, right? By picking x to be 1/2, and then expand the idea on the right-hand side. So similar thing to the left-hand side, right? So and then you move everything to the other side to solve for ln2, and then you get that ln2 can be rewritten as an infinite sum, right? So this is some technique that people use to use for a power series, is to represent a an irrational number with an infinite sum of rational numbers. Okay. All right. So that's it for 10.7 power series. It's a really long video, so definitely take your time on the homework, and then feel free to rewatch it again. Thank you guys very much. I'll see you next time.